We're going to cover how to solve the Brachistochrone problem in Python. So come to the APMonitor.com website and either type in wiki there, or you can come over here to the documentation. And this one is just posted here on the right under examples. If you just go to dynamic optimization, and then it'll be under the Brachistochrone link here. Okay, so this is a classic optimal control problem to compute this curve. So if you have a ball that has no friction and you release it, what is the shape of that curve that's going to get that point mass to the end the fastest? And so there are a couple equations that govern the motion, and then we're also going to try to minimize the final time. Okay, so here are the equations. We're going to minimize TF, which is final time, subject to the first equation, which is the x position. So it's the velocity in the x direction equals velocity times sine u. U is the value, the incline of the slope at that particular point in time. Okay, and then we have also the the equation here for y. Now that's just going to be cosine instead of sine, and then we also have the equation for the velocity, or dv dt is the acceleration, and that's related to the gravity, the constant g. Okay, so there are some initial conditions here. The x and y positions initially are at 0, and the velocity is initially 0 as well. And at the final time, we need to be at a position of 2 for x and 2 for y. Now y in this case is in the down direction. So we've just defined y positive is going down, just for convenience here. Okay, so here is the solution right here, but I'd say first of all, go ahead and pause the video and see if you can work through it on your own, and then continue on here if you need some help. Okay, so the solution, go ahead and download it. It's going to be an archive here, a zipped archive. And once you've downloaded it, come to your downloads folder, and I'm just going to copy that back onto my desktop. Now this was provided by Trent Okeson. He worked through this problem and did it in kind of an innovative way that I wanted to show you here. So here are the equations right here. We have this scaling factor, the time scaling, so that we initially start with 1, but then it's able to minimize that final time, and we've adjusted the differential equations here to automatically expand or contract that horizon. Okay, and then what this solution does is it takes the final time and then also includes in the objective function any distance that you're not at 2 for x and 2 for y. Okay, so we do x minus 2 and then we square it, and we only want to penalize that at the final time, and do the same thing for y as well. Okay, so let's go ahead and run this problem. I'm going to open up this Python script, main.py, open up with the IDLE editor. Okay, and then go ahead and run with F5, and so it's going to solve this and then come back with a couple plots that show us the solution. So okay, so here is the solution. It took 41 iterations with the IPOP solver. You can see that was about just a little over 2 seconds. Okay, so let's get into the solution a little bit here. We have the position in the negative y direction, okay, and then also the x direction right here. The x-axis is the x position. And then we also have the angle. That's a thing that we could adjust over the time horizon. It went up to about 8.2, 8.3 seconds. And so this is an optimal shape. If you were to put the this mass point here, it would slide down, and that would be the minimum time. So I also extended this script just a little bit to see what it would do if I changed the final point. So come back here. Here's the solution to the first one, the originally given problem. But let's say you wanted to change this final condition right here. Okay, so change that to between 1 and 10, for example. Okay, and so the solution to that is if we wanted to vary the final position, the solution to that is given here. So you can see there are different shapes for different final conditions. So if you're going further out, then it says, go dip down, and then it'll come back up at the end. So you pick up some additional velocity, even though you're traveling a little further. This is going to be the minimum time solution. So you can also download that one as well. I'll just go ahead and show this, running. And okay, so this is the X-end study, and I'll show you what I did to just add this extra parameter in there to study the effect of this. Okay, so I just updated this model. So instead of a 2 here, I just put X-end, and then I put X-end as a parameter. Okay, let me go back into the script, and I'll just show that as well. I'm going to come in here to the main.py and go ahead and edit that, and then I just put this in a loop, and then I just inserted different values of X-end. I first of all did a linearly spaced region between 1 and 10 with 10 different points, and then just put in the different values of X-end, and then solved it. And then for each loop I went ahead and plotted the solution. So let's go ahead and run that, and you could change X-end, or you could set up a Y-end as well, and that would essentially give you different ending points. Okay, so it's going to run through all of these 10. You can see them run one at a time, and then as a final point it's going to pop up with this this trend that we had before. Okay, so this is the optimal shape if you have different these final positions between 1 and 10, but y always has to equal 2, or in the down direction it'd be -2. Okay, so this is the solution to that problem in Python. What we've been doing is doing some of these challenge problems. We'll post another one, some more of these challenge problems here. We had last week, we had the rocket launch, and we'll do another one next week as well.